Very good morning, students. So already we completed the theoretical part of electric potentials. Based on that electric potential, we have very few problems as far PUC is concerned. Today we'll finish off those problems based on electric potential. Note down the first problem. The first problem, two charges 5 into 10 to the power of minus 8 coulomb and minus 3 into 10 to the power of minus 8 coulomb are located 16 centimeter apart. Are located 16 centimeter apart. Full stop. At what points on the line joining the two charges is the electric potential zero. Is the electric potential zero. Now, what is given is two charges Q1 and Q2 are separated by a certain distance. Now he is asking us to find at what point the electric potential is zero. So as we discussed already, at 2 points the electric potential will be zero. One is between these two and one is outside of those two. So first case I am taking at the point P, which is at a distance of x, the electric potential is zero. I am considering at the point P the electric potential is zero. At P, how many electric potentials will act? Two electric potentials will act. One is because of this charge, other is because of this charge. If V1 be the potential, let V1 be the potential, at P due to charge Q1. Let V1 be the potential at P due to charge Q1. So V1 is equal to 1 by 4 pi epsilon naught Q1 by X, which is equal to 9 into 10 to the power of 9. Q1 value is 5 into 10 to the power of minus 8 divided by X. Call it as equation 1. Next time, let V2 be the potential. Let V2 be the potential at P due to the charge Q2. V2 is equal to, again, 1 by 4 pi epsilon naught Q2 by this distance we should take. which is equal to r minus x. Now, which is equal to 9 into 10 to the power of 9 Q2 value. As we discussed, if charge is negative, we have to consider negative only, because the potential due to negative charge is negative potential. So minus 3 into 10 to the power of minus 8 divided by r minus x. R is in centimeter. If you convert into meters, 0.16. So I can write it as 0.16 minus x. 0.16 minus x. The total potential at P now. The total potential at P. Since the potential is a scalar quantity, directly by adding V1 and V2, we'll get the total potential. We know that potential at P is 0. Potential at P is 0. If I make use of that, we are going to have 9 into 10 to the power of 9, 5 into 10 to the power of minus 8 by x is equal to 9 into 10 to the power of 9, 3 into 10 to the power of minus 8 divided by 0.16 minus x. 9 into 10 to the power of 9, 9 into 10 to the power of 9 get cancels. 10 to the power of minus 8 and 10 to the power of minus 8 get cancels. 5 by x is equal to 3 by 0.16 minus x. If you cross multiply 16 5s are 80, 16 5s are 80, so 0.8 minus 5x is equal to 3x. So 8x is equal to 0.8, x is equal to 0.1 meter, which is equal to 10 centimeter. The first case is the point which is at a distance of 10 centimeter from Q1 towards Q2, the electric potential will be 0. But as we discussed in previous classes, both the cases we have to find, because there is a possibility to get the potential as 0 in two scenarios, two situations. One is inside and one is outside. So both the positions you have to find. So this is the point where I am considering inside or between Q1 and Q2. Now, copy it. Now, I am taking the point outside. I am taking the point outside. I am taking the point outside now. This is the point which is at a distance of x. Now the same method. Let V1 be digicom, V2 be digicom. So here, instead of r minus x, what is the distance of Q2 to the point P? R plus x. So here, while finding the V2 value, we should consider r plus x. Here is also r plus x. Here is also 0.16 plus x. 0.16 plus x. 0.8 plus 5x. 0.8 minus 2x. X is equal to x is equal to 0.8 by 2, which is equal to minus 0.4 meter, which is equal to minus 40 centimeter. Here minus symbol indicates that if I consider the position of Q1 as an origin, so left side of the origin, so left side of Q1 will be always negative value. So here minus 40 centimeters indicating that the zero potential point will be at a distance of 40 centimeter from Q1 towards its left. The zero potential point is at a distance of 40 centimeter from Q1 towards left. Like that, you should write the statement. First you copy this. What I should write? The point P will be at a distance of 40 centimeter from Q1 towards its left, towards its left. Like that easily we can solve. But the thing here is, both the positions you have to find, because there is a possibility to get the zero potential at both the positions. We have to find with both. Next, second problem. A regular hexagon of side 10 centimeter, has a charge 5 microcoulomb at each of its vertices. Full stop. Calculate the potential at the center of the hexagon. Now he is considering a beautiful hexagon of side 10 centimeter, or side A. In fact, a charge Q is placed at all the 6 corners of an hexagon. where Q is equal to 5 microcoulomb, that is nothing but 5 into 10 to the power of minus 6 coulomb. A is equal to 10 centimeter, which is equal to 0.1 meter, which is equal to 0.1 meter. Now he is asking us to find what will be the total electric potential at the center of an hexagon. So this we call it as the center. This is the center. Center of an hexagon. Now, as we know, the center point in a hexagon is equidistant to all the corners. Equidistant to all the corners. And the distance of the center from the corner will be always equal to the side in case of an hexagon. That is nothing but this distance is also a, 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 a. So the distance of the center from all the corners, from each corner is the same, which is equal to a. So here at O, how many potentials will act? Because of the 6 charges, 6 potentials will act. Because of this 1, 2, 3, 4, 5, 6. Because of the 6 charges, 6 potentials will act. What is the general formula to find out potential? V is equal to 9 into 10 to the power of 9 Q by R is the general formula. In all the 6 cases, the charge is same. In all the 6 cases, the distance is also same. So the total potential, that is nothing but the potential at O because of this is equal to, next one like this, V1 is equal to, V2 is equal to, V3 is equal to, V4 is equal to, V5 is equal to, and is equal to V6. V1 is equal to, V2 is equal to, V3 is equal to V6. Then because of the potential is a scalar quantity, we can add them to get the total potential at O is equal to V1 plus V2 plus V3 plus V4 plus V5 plus V6. So as we know, V1 is equal to V2 is equal to 0. So we are going to have 6V1. Because of V1 is equal to V2 is equal to V3 is equal to like this. 6 V1 value 9 into 10 to the power of 9 Q value is 5 microcoulomb. 5 into 10 to the power of minus 6 divided by R value. R value is equal to A here, where A is equal to 0.1. So 5 6s are 30, 39s are 270. 270 into 10 to the power of 4. If minus 1 goes, it will become 10 to the power of 10, minus 6, 10 to the power of plus 4. Otherwise, 27 into 10 to the power of 5 volt. So the total potential at O is equal to Next, third problem. Third problem. Two charges, 2 microcoulomb, 2 microcoulomb and -2 microcoulomb and -2 microcoulomb are placed at points A and B, 6 centimeter apart. 6 centimeter apart. In that first one, identify an equipotential surface. Identify an equipotential surface of the system. Second one, what is the direction of electric field? What is the direction of electric field at every point? What is the direction of electric field at every point on this surface? On this surface. So in the problem, what is given is two charges he considered. One is 2 microcoulomb and another one is -2 microcoulomb, separated by a certain distance. Then he is asking us to identify the equipotential surface. How will you identify what is equipotential surface? The surface at which the potential is same at all the points. The surface at which the potential is same at all the points. Already we discussed, by seeing this diagram, because of two equal and unlike charges separated by a certain distance, it will looks like a dipole. So in case of a dipole, the formula to find out the potential, V is equal to 1 by 4 pi epsilon naught P cos theta by R square. P cos theta by R square. Now, what will happen is, you take a point anywhere, either you take the point here or here or here, then what will happen? The R value will changes. Or if you take the point here, here like this, the theta value changes. So then we know that in case of an electric dipole, the potential will be 0 at the equatorial line. So what is an equatorial line? Perpendicular bisector. So for example, so like this, now this is the plane what I am considering on an equatorial line. Whatever the point you choose, there the potential is 0, because at every point on the equatorial line of an electric dipole, the potential is a constant and is equal to 0. So whatever the point you take on equatorial plane, then the potential is 0. So I can say this plane as, or this surface as, an equipotential surface. Why? Because the potential is same at all the points whose value is 0. Okay. So for the first one, the answer is the surface in a equatorial plane of an electric dipole, equatorial plane of an electric dipole, the potential at all the points is same. The potential at all the points is same and is equal to 0. The potential at all the points is same and is equal to 0. That is called as an equipotential surface. Now, while discussing equipotential surface, we discussed that. So, at any point on the equipotential surface, what are the points we discussed? Equipotential surfaces will be always concentric, and the angle between the equipotential surface and the direction of electric field is 90°, and the equipotential surfaces will never intersect, and the work done to move any charge from one point to another point in an equipotential surface is 0. These are the points we discussed. So here is also, if it is an equipotential surface, the angle between the equipotential surface and electric field is 90°. That is the second one what is asked. So for the second one, the answer is 90°. Next problem. A spherical conductor, fourth problem. A spherical conductor of radius 12 centimeter, a spherical conductor of radius 12 centimeter, has a charge of 1.6 into 10 to the power of minus 7 coulomb, distributed uniformly on its surface. Distributed uniformly on its surface. Full stop. What is the electric field and potential? What is the electric field and potential first one? At a point, what is the electric field and potential? First one. At a point 18 centimeter from the center of a sphere. At a point 18 centimeter from the center of the sphere. Now, this is a sphere of radius r, where r is equal to 12 centimeter. Now I want to find out the electric intensity and electric field at a distance of 18 centimeter from the center. Under a small r value 18 centimeter. From here we come to know that small r is greater than capital R. Now he is asking us to find somewhere at the point P is outside now. What is an electric intensity and electric potential? Electric intensity E is equal to 9 into 10 to the power of 9 q by small r square. Q by small r square. So 9 into 10 to the power of 9. Q value is 1.6 into 10 to the power of minus 7 divided by R. R is 18 centimeter, which is equal to 0.18 meter. 0.18 meter. So 0.18 into 0.18. Now which we can write it as 9 into 16. If I write 16 here, it is the 10 to the power of minus 8. So here we'll get a 10 divided by 18 into 18 into 10 to the power of minus 4. 9 ones, 9 twos, 2 eights. Then 4 by 9. 4 by 9 into 10 to the power of 5. So 0.40, 9 fours are 36, 40, 0.44 recurring is the electric charge. Sorry, electric field, electric intensity. 0.44 into 10 to the power of 5. Then electric potential. What is the formula? At the same point, I want to find the electric potential. Vp is equal to 9 into 10 to the power of 9 q by r. 9 into 10 to the power of 9 q value 1.6 into 10 to the power of minus 7. So 16 into 10 to the power of minus 8. Small r value 18 centimeter. You make it into meters. 18 into 10 to the power of minus 2. 9 ones, so 9 twos, so 2 eights. So 8 into 10 cube volt. 8 into 10 cube volts. Next, second one. Just second one, next, second one. Just outside the sphere. Second one, just outside the sphere. Just outside the sphere. He is taking the point just outside the sphere. So that is nothing but small r is equal to capital R, which is equal to 12 centimeter. Now the same procedure. Electric intensity at a P, 9 into 10 to the power of 9 q by capital R square. 9 into 10 to the power of 9. Q value is 1.6 into 10 to the power of minus 7. R value is 12 centimeter. Square is there. 0.12 into 0.12. 9, 16 into 10 by 12 into 12 into 10 to the power of minus 4. Now 4 fours, 4 threes, 3 ones, 3 threes, 12, 12. So finally 10 to the power of 5 Newton per coulomb. Similarly, the electric potential now. The electric potential now. Vp is equal to 9 into 10 to the power of 9 Q by capital R I should take. Capital R. Which is equal to 9 into 10 to the power of 9. Q value is 1.6 into 10 to the power of minus 7 divided by capital R value 12 into 10 to the power of minus 2, which is equal to 9 into 16 into 10 divided by 12 into 10 to the power of minus 2, 3 4 fours, 4 threes, 3 threes, 3 nines. So 12 into 10 cube volt. 12 into 10 cube volts will be the potential just outside the sphere. Will be the potential just outside the sphere. Third one. Third one. Third one. Third one. Inside the sphere. The point P is inside the sphere. Inside the sphere. So R value is lesser than capital R inside the sphere. So somewhere here the point P is there inside the sphere. Then as we know, inside the sphere, as we know, inside the sphere, the electric intensity is 0 according to Gauss theorem we derived. So electric intensity is 0. Inside the sphere, the electric intensity is 0. Next, what about the potential? That also we derived recently. Okay. Next slide. Inside the sphere, the potential is constant. The potential is constant and same as on its surface. And same as on its surface. That is nothing but how much potential will be there at the surface, the same potential will be there inside also. Now the same formula. Vp is equal to 9 into 10 to the power of 9 Q by R. With this, we'll conclude the potential, and one more topic called as a capacitor we'll discuss from tomorrow. Thank you.